Welcome to this video on the trapezoidal rule. I'm going to explain the theory behind the rule, and I'm going to demonstrate how we can use the rule in an example problem and solution. I'll also discuss error estimates for the trapezoidal rule. If you're already familiar with the theory behind the rule, and you'd like to see the rule demonstrated in an example problem and solution, or if you'd like to learn about error estimates, please use the timestamps in the description below to skip ahead to that part of the video. An example of a trapezoid is shown below. We can calculate the area of this trapezoid using the following equation. The area is equal to a half multiplied by left bracket C plus D right bracket multiplied by H. The trapezoidal rule is a numerical method that can be used to approximate the definite integral of a function. When we want to evaluate the definite integral of a function f, but we cannot find a suitable antiderivative F to use, we can use the trapezoidal rule to approximate the definite integral. The integral from a to b of a function f of x with respect to x is equal to the net area between the function curve and the x-axis on the closed interval from a to b. When we calculate net area, we count area above the x-axis as positive and area below the x-axis as negative. The trapezoidal rule can be used to estimate this value of net area by using a sum of the areas of trapezoids, counting area below the x-axis as negative. We can use this estimate of net area to approximate the integral from a to b of the function f of x with respect to x. The trapezoidal rule is now shown here. We can use t to approximate the integral from a to b of f of x with respect to x. T is equal to h over 2 multiplied by left bracket y naught plus 2y1 plus 2y2, adding terms up to 2yn minus 1, and then adding yn, right bracket. H is equal to b minus a divided by n. The y values are the values of the function f at the partition points, with x0 equal to a, x1 equal to a plus h, and x2 equal to a plus 2 multiplied by h, and with xn minus 1 equal to a plus left bracket n minus 1 right bracket multiplied by h, and xn equal to b. I'll discuss and explain this rule further now. Shown below is a plot of the continuous function f of x on the closed interval from a to b. We can partition the closed interval from a to b into n subintervals of equal length h. Each subinterval length h is equal to b minus a divided by n. We refer to the subinterval length h as the step size. We can approximate the function curve on the closed interval from a to b by using a straight line segment over each subinterval. We can estimate the area between the function curve and the x-axis over a subinterval by using the area of the trapezoid, which is formed by joining the ends of the straight line segment for that subinterval to the x-axis. The area of the trapezoid in the first subinterval is equal to a half multiplied by left bracket y0 plus y1 right bracket multiplied by h. The point x0, y0 is now highlighted on the graph below. The value y0 is the length of the line segment now highlighted. The point x1, y1 is now highlighted on the graph. The value y1 is the length of the line segment now highlighted. The value h is the length of the line segment now highlighted. The area of the trapezoid in the second subinterval is equal to a half multiplied by left bracket y1 plus y2 right bracket multiplied by h. The value y1 is the length of the line segment now highlighted. The point x2, y2 is now highlighted on the graph. The value y2 is the length of the line segment now highlighted. The value h is the length of the line segment now highlighted. We sum the areas of the trapezoids, counting area above the x-axis as positive and area below the x-axis as negative. T is equal to a half multiplied by left bracket y0 plus y1 right bracket multiplied by h plus a half multiplied by left bracket y1 plus y2 right bracket multiplied by h, adding terms up to a half multiplied by left bracket yn minus 2 plus yn minus 1 right bracket multiplied by h, and then adding a half multiplied by left bracket yn minus 1 plus yn right bracket multiplied by h. The expression now highlighted is equal to the net area of the trapezoid, which is on the subinterval from x0 to x1. The expression now highlighted is equal to the net area of the trapezoid, which is on the subinterval from x1 to x2. The expression now highlighted is equal to the net area of the trapezoid, which is on the subinterval from xm-2 to xm-1. And the expression now highlighted is equal to the net area of the trapezoid, which is on the subinterval from xm-1 to xn. If the line segment for a subinterval crosses the horizontal axis, as is currently highlighted below, the line segment for that subinterval won't create a four-sided trapezoid like the ones over the other subintervals shown below. However, the net area between the line segment currently highlighted and the horizontal axis still provides an estimate of the net area between the function curve and the horizontal axis over that subinterval. We still calculate the net area between the line segment and the horizontal axis for that subinterval as being equal to the average of the y values at the beginning and end of that line segment multiplied by h. We still include the net area between the line segment and the horizontal axis for that subinterval in the sum now highlighted. This expression, now highlighted, is equal to h multiplied by left bracket a half multiplied by y0 plus y1 plus y2, adding terms up to y n-1, and then adding a half multiplied by yn, right bracket. This is equal to h over 2 multiplied by left bracket y0 plus 2y1 plus 2y2, adding terms up to 2y n-1, and then adding yn, right bracket. This equation, now highlighted, is the equation that we use to approximate the value of a definite integral when we use the trapezoidal rule. y0 is equal to f of a, y1 is equal to f of x1, yn-1 is equal to f of x n-1, and yn is equal to f of b. To explain this highlighted equation further, if we partition the closed interval from a to b into 5 subintervals, then n would be equal to 5, and t would be equal to h over 2 multiplied by left bracket y0 plus 2y1 plus 2y2 plus 2y3 plus 2y4 plus y5, right bracket. Next, I'll demonstrate the use of the trapezoidal rule in an example problem and solution. In this example problem and solution, I want to use the trapezoidal rule to estimate the integral from 1 to 5 of 8x minus x squared with respect to x. A plot of the function f of x equal to 8x minus x squared on the closed interval from x equal to 1 to x equal to 5 is now shown to the right. In this example, I'm going to partition the closed interval from 1 to 5 into 4 subintervals. I'll be estimating the definite integral from 1 to 5. So a is equal to 1 and b is equal to 5, and I'll be using 4 subintervals, so n is equal to 4. the step size h is equal to b minus a over n, which is equal to 5 minus 1 over 4, which is equal to 4 over 4, which is equal to 1. Next, I want to calculate the x-axis values at the partition points. Once I have these values, I'll use them to calculate the y values at the partition points. x0 is equal to a, which is equal to 1. x1 is equal to a plus h, which is equal to 1 plus 1, which is equal to 2. x2 is equal to a plus 2h, which is equal to 1 plus 2 multiplied by 1, which is equal to 3. x3 is equal to a plus 3h, which is equal to 1 plus 3 multiplied by 1, which is equal to 4. And x4 is equal to b, which is equal to 5. Now I'll calculate the y values at the partition points. y0 is equal to f of x0, which is equal to 8 multiplied by 1 minus 1 squared, which is equal to 7. y1 is equal to f of x1, which is equal to 8 multiplied by 2 minus 2 squared, which is equal to 16 minus 4, which is equal to 12. y2 is equal to f of x2, which is equal to 8 multiplied by 3 minus 3 squared, which is equal to 24 minus 9, which is equal to 15. y3 is equal to f of x3, which is equal to 8 multiplied by 4 minus 4 squared, which is equal to 32 minus 16, which is equal to 16. And y4 is equal to f of x4, which is equal to 8 multiplied by 5 minus 5 squared, which is equal to 40 minus 25, which is equal to 15. Next, I'll calculate the value of t. In this example, I've chosen n to be equal to 4. So t is equal to h over 2 multiplied by left bracket y0 plus 2y1 plus 2y2 plus 2y3 plus y4 right bracket. This is equal to a half multiplied by left bracket 7 plus 2 multiplied by 12 plus 2 multiplied by 15 plus 2 multiplied by 16 plus 15 right bracket. This expression, now highlighted, is equal to the sum of the net areas of the trapezoids, now highlighted on the graph. This expression, now highlighted, is equal to a half multiplied by left bracket 7 plus 24 plus 30 plus 32 plus 15 right bracket. This is equal to a half multiplied by 108, which is equal to 54. I've now estimated that the integral from 1 to 5 of 8x minus x squared with respect to x is equal to 54. This concludes this example problem and solution. Next, I'll discuss error in the trapezoidal rule approximation. If the function f has a continuous second derivative, then the magnitude of the error in the trapezoidal approximation will decrease as the step size h decreases. If the second derivative f double prime is continuous, and m is any upper bound for the absolute value of f double prime on the closed interval from a to b, then the absolute value of the error in the trapezoidal rule approximation is less than or equal to b minus a over 12 multiplied by h squared multiplied by m, where the step size h is equal to b minus a over n. We can use this equation now highlighted to estimate the error in trapezoidal rule approximations. I'll also mention here that it is possible for round-off errors to affect trapezoidal rule approximations in a significant way. This can occur if the step size h is set so small that round-off errors accumulate and become significant. In these situations, error estimates using the equation currently highlighted may no longer be accurate. Next, I'll estimate the error in a trapezoidal rule approximation in an example problem and solution. In this example, I want to find an upper bound for the error in the trapezoidal rule approximation of the integral from 1 to 5 of 8x minus x squared with respect to x, with n equal to 4. The trapezoidal rule is being used on the closed interval from 1 to 5, so a is equal to 1 and b is equal to 5. The step size h is equal to b minus a over n, which is equal to 5 minus 1 over 4, which is equal to 4 over 4, which is equal to 1. The function f of x is equal to 8x minus x squared. F prime of x is equal to the derivative of 8x with respect to x minus the derivative of x squared with respect to x. The derivative of 8x with respect to x is equal to 8, and the derivative of x squared with respect to x is equal to 2x. So f prime of x is equal to 8 minus 2x. F double prime of x is equal to the derivative of 8 with respect to x minus the derivative of 2x with respect to x. The derivative of 8 with respect to x is equal to 0, and the derivative of 2x with respect to x is equal to 2. So f double prime of x is equal to 0 minus 2, which is equal to minus 2. The absolute value of f double prime of x is equal to the absolute value of minus 2, which is equal to 2. Now that I've calculated the absolute value of f double prime of x, I want to assign a value to the variable m. I want the value of the variable m to be an upper bound of the absolute value of f double prime of x on the closed interval from 1 to 5. The absolute value of f double prime of x is equal to 2 on the closed interval from x equal to 1 to x equal to 5, so I can set m equal to 2. The absolute value of the error in the trapezoidal rule approximation is less than or equal to b minus a over 12 multiplied by h squared multiplied by m. This is less than or equal to 5 minus 1 divided by 12 multiplied by 1 squared multiplied by 2. This is less than or equal to 4 over 12 multiplied by 2, which is less than or equal to 0.67, rounded to 2 decimal places. I've now calculated that the absolute value of the error in the trapezoidal rule approximation is less than or equal to 0.67. This concludes this example problem and solution. To summarize, the trapezoidal rule is a numerical method that can be used to approximate the definite integral of a function. In this video, I've described the theory behind the rule, and I've demonstrated the use of the rule in an example problem and solution. I've also discussed error estimates in trapezoidal rule approximations and demonstrated these estimates in an example problem and solution. If you found this content useful, please subscribe to the channel to receive more content. Thank you very much for watching this video. See you next video.